This is SpaceTime Series 19, Episode 23, being broadcast on the 19th of October 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the universe has over 20 times more galaxies than previously thought. How Pluto paints its largest moon red. And China launches 2 taikonauts on a month-long mission in space. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has concluded there are at least 2 trillion galaxies, some 20 times more than previously thought, in the observable universe. The findings, reported in the Astrophysical Journal, are based on a new study of data from the Earth-orbiting Hubble Space Telescope as well as other ground and space-based observatories. The data from the Great Observatory's Origins Deep Survey, or GOODS, is the most accurate census of the number of galaxies across the cosmos ever undertaken. As well as having implications for science's understanding of galaxy formation, the results also help to solve an ancient astronomical paradox. Namely, with all the stars around, why is the sky dark at night? One of the most fundamental questions in astronomy is just how many galaxies does the universe contain? Images, including the Hubble Deep Field, the Hubble Ultra Deep Field and the Hubble Deep Field South, have provided astronomers with their first real insights into this question by showing them a glimpse of the myriad of faint galaxies revealed in just one tiny section of the sky. It allowed scientists to estimate that the observable universe contains something like 100 billion galaxies. But there's a problem. You see, the limited speed of light, namely 300,000 kilometers per second in a vacuum, combined with the age of the universe, just 13.8 billion years, means that based on the universe's expansion out from the Big Bang, limited by gravity, and multiplied by the estimated accelerated expansion dark energy has had on spacetime, means that only a tiny fraction of the estimated 93 billion light-year-wide size of the universe can ever be seen from Earth. This small window is known as the cosmological horizon. Now, a study led by Christopher Kinsellas from the University of Nottingham has shown that this 100 billion galaxy estimate is at least 10 times and more likely 20 times too low, meaning that the cosmos contains at least 2 trillion galaxies. Kinsellas and colleagues reached their conclusion after painstakingly converting their telescope images into 3D in order to make accurate measurements of the numbers of galaxies at different times through the universe's history. They also used new mathematical models which allowed them to infer the existence of galaxies which the current generation of telescopes simply can't see. This led to the surprising realization that in order for the numbers to add up, at least 90% of the galaxies in the observable universe are actually too faint and too far away to be seen. Kinsellas says it boggles the mind that over 90% of galaxies in the universe are yet to be studied. In analysing the data, Kinsellas and colleagues looked more than 13 billion years into the past. This showed them that galaxies weren't evenly distributed through the universe's history. In fact, it appears there were a factor of 10 to 20 more galaxies per unit volume of the universe when the universe was just a few billion years old compared to today. Most of these galaxies were relatively small and faint, with masses similar to those we see in the satellite galaxies surrounding the Milky Way today. These results are powerful evidence that a significant evolution's taken place throughout the universe's history, with galaxies constantly merging together, dramatically reducing their total number. The findings therefore provide verification for the so-called top-down formation of structure in the universe. This decreasing number of galaxies as time progresses also contributes to the solution of Olbers' paradox, why the sky is dark at night. The astronomer Heinrich Olbers argued that the night sky should be permanently flooded by light. That's because he thought there was an unchanging universe filled with an infinite number of stars, so every single part of the sky should be occupied by a luminous object. However, our modern-day understanding of the universe tells us that it's not infinite and static, but is in fact finite and dynamic. Concelis and colleagues found that there is in fact such an abundance of galaxies that in principle at least every single point in the sky should contain at least part of a galaxy. However, most of these galaxies are invisible to the human eye and even to modern telescopes, owing to a combination of factors including the redshifting of light due to the universe's dynamic nature and the absorption of light by intergalactic dust and gas, all combining to ensure that the night sky remains mostly dark. Well, it seems Pluto's binary partner and largest moon, Charon, owes its unusual reddish colouring to methane gas escaping Pluto's atmosphere and becoming trapped by Charon's gravity, eventually freezing onto its cold, icy surface. The findings, reported in the journal Nature, resolve a mystery which began in June 2015, when cameras on NASA's Approaching New Horizons spacecraft first spotted the large reddish polar region on Charon. Mission scientists had never seen anything quite like this before. So, in order to try and solve the mystery, scientists have spent the last year analysing the images and other data sent back by New Horizons following its historic 2015 flight through the Pluto system. Researchers found that the chemical processing by ultraviolet light from the sun transforms the methane into heavier hydrocarbons and eventually into reddish organic materials called tholins. The study's lead author, Will Grundy, from the Lowell Observatory in Flagstaff, Arizona, says who would have thought that Pluto's a graffiti artist, spray painting its companion red. To reach their conclusions, the team combined analyses from detailed Charon images obtained by New Horizons with computer models of how ice should evolve on Charon's poles. Mission scientists had previously speculated that methane in Pluto's atmosphere was trapped in Charon's North Pole and slowly converted into the reddish material. The New Horizons team dug through the data to determine whether conditions on Charon would allow the capture and processing of methane gas. The models, using Pluto and Charon's 248 Earth-year orbit around the Sun, show some extreme weather at Charon's poles, where 100 Earth-years of continuous sunlight alternate with another century of continuous darkness. Surface temperatures during these long winters can dip to minus 257 degrees Celsius, cold enough to freeze methane gas into a solid. The methane molecules bounce around on Charon's surface until they either escape back into space or land on the cold polar regions where they freeze solid, forming a thin coating of methane ice that lasts until sunlight comes back in the spring. But while the methane ice quickly sublimates away, the heavier hydrocarbons created from it remain on the surface. The models also suggest that in Charon's springtime, the returning sunlight triggers conversion of the frozen methane back into a gas. But while the methane ice quickly sublimates away, the heavier hydrocarbons created by this evaporative process remain on the surface. Then sunlight further irradiates these leftovers into reddish material called tholins that have slowly been accumulating on Charon's poles for millions of years. New Horizons observations of Charon's other pole, which is currently in winter darkness and only seen by New Horizons through light reflecting from Pluto, or Pluto shine, confirmed that the same activity was occurring at both poles. New Horizons principal investigator and study coordinator Alan Stern from the Southwest Research Institute says the study not only solves one of the greatest mysteries found on Charon, but also opens up the possibility that other small planets in the Kuiper Belt with moons may create similar or even more extensive atmospheric transfer features on their moons. Although often referred to as the largest of Pluto's 5 known moons, the 1,212-kilometre-wide Charon is actually Pluto's binary partner and a dwarf planet in its own right. The two worlds orbit each other around a common centre of gravity. Prototype software developed to manage data from the Square Kilometre Array Telescope project is now being tested on the world's second fastest supercomputer in China. Once installed on the SKA, the complete system will process raw observations from distant stars and galaxies and turn them into data that can be studied by astronomers around the world. Professor Andreas Wesenek from the University of Western Australia's arm of the International Centre for Radio Astronomy Research says the Square Kilometre Array Science Data Processor will be the brain of the new radio telescope now being built in outback Australia and southern Africa. The successful deployment of the prototype Science Data Processor Execution Framework on the Tianyi 2 supercomputer provides the control and monitoring environment to execute millions of tasks, consuming and producing millions of data items on many thousands of individual computers. This is important because it represents the scale of computer processing required for every single square kilometre array observation obtained every 6 to 12 hours. Wesenek says the novel execution framework on the Science Data Processor is data activated, meaning individual data items are wrapped in an active piece of software that automatically triggers the applications needed to process it. Whenever a data item's ready, it triggers the next task. The prototype was initially run on 500 compute nodes at the supercomputer and then extended to 1,000 nodes. The next step will be to ramp up the number of individual items being deployed and then increase the number of compute nodes to around 8,500. The system's already running 66,000 items, and the next stage will be to increase that to several million. The plan involves eventually running 50 to 60 million items on between 8,500 and 10,000 nodes. Located in China's Ganzhou, Tianyi 2 has some 16,000 computer nodes and can perform quadrillions of calculations every second. In fact, until surpassed this year, it was the world's fastest supercomputer from June 2013 until June 2016. The Square Kilometre Array is one of the world's largest science projects, with the low-frequency part of the telescope alone set to have more than 250,000 antennas facing the sky. Wesenek says each of the 2 Square Kilometre Array observatories will produce enough data to fill a typical laptop hard drive every second.
We'll have a dedicated, on-purpose built computing facility on site, on both sides, actually in South Africa and in Western Australia. And they are doing essentially add and multiply very simple things, and that's FPGA-based machines. And that stage, the data is even much more than what we are receiving for the processing. Now, after that stage, the data is going onto a wide area network. In both cases, about 800 kilometers network, down to dedicated compute centers, and that's mostly high-performance compute facilities and common off-the-shelf hardware. That's what we are planning at least, or at least mostly common off-the-shelf hardware. And what we are getting through the network in both cases, South Africa and Western Australia, will be about 1 terabyte a second. That means a typical hard drive on a laptop right now would be filled within 1 second. So that's probably explaining best what scale of magnitude we have to deal with, and that's a wide area network as well.
The astronomers who are going to be sifting through that data, that's going to be too much for any team to go through. There've got to be ways of working out through some automated process what you keep and what you throw away.
Yeah, that's correct. So actually at that stage, nobody will actually look at the data directly because it's simply too much. So that's where the SK is very different, and for that matter, the Australian Square Kilometre Pathfinder, the ASCAP telescope, is very similar. So the data from that Pathfinder is already so big that we have to process it straight away in an automatic fashion. And the SK is even more so. So what we are really planning to do is take that data, which up to now is actually dealt with directly by astronomers in current-day telescopes, and turn it around and produce higher-level data products out of that, which are much smaller than and easier to handle. So the plan is to have essentially no people really interacting with the data directly, but only the automated systems and computers, and then have only a few quality checkpoints which tell us whether the data is any good or whether the reduction went correctly.
And then from there it goes to the astronomers to actually work out what they're seeing and what that means for their theories.
Exactly.
Tell me about the work your team has been doing with what was once the fastest computer in the world, now still the second fastest. Might point out at this stage China has, I think, about 5 of the 10 fastest computers in the world at the moment.
Yep, so they are quite active in that area, and it's quite an opportunity to actually be able to tap on those resources, which are quite a bit away from many of the next ones. The first one is now close to 100 petaflops. The second one is still on a 50 petaflop scale, so it's huge resources we can actually use there.
Perfect example of Moore's law.
Yeah, absolutely. If you look at the top 500 list, we're actually on a kind of a flat plateau the last 4.5 years with the system we had been using now, and that brought us underneath the logarithmic scale, which Moore's law is actually giving us. But with the new system, we are exactly on top that line again. You can see it theirs straight away.
And we've got atomic hard drives still to come. That's being worked on now.
Exactly, yeah.
Tell me about the research that you've been involved in.
What we are responsible for inside the so-called science data processor work package of the square kilometer array is what's called the data layer. And the data layer is essentially everything which deals with managing the data from the point when we receive it from the wide area network, from the site, from the two sites, throughout the life cycle of the data when it's being distributed to astronomers. So this is really about data management, data life cycle management, and the controlling the processing. We are not too much involved in the processing algorithms themselves. That's kind of modules in our system, but we have been working a lot on getting a framework in place where we can actually execute those algorithms.
And the computer you're using got 16,000 computer nodes?
Yes, a really big one, and for the time being we haven't even used a large fraction, but that's the next stage. So we are planning on using up to 10,000 or even more of those nodes.
And this is really the sort of level we have to be looking at in order to process all this information that the SKA, both in Australia and South Africa, will be providing.
Yes, each of those facilities in Cape Town at the end of the day and in Perth will be of about that order of magnitude in size. And order of magnitude in size means number of nodes, because at the time when we are building those computers, of course, they are much more powerful. So we'll take advantage of Moore's law again and use essentially the same number of nodes, but with a lot more power in the back. The framework we have actually been working on is very flexible. So what we can do is not just run it on these very, very big computers. We actually run it on a single computer as well. And moreover, we also run it on the cloud. So we can actually export that whole thing into things on Amazon Web Services, on similar cloud infrastructures. And that gives us the ability to support our astronomy community even better than just by supporting the main infrastructure of the SKA.
That's Professor Andreas Wesenek from the University of Western Australia's arm of the International Centre for Radio Astronomy Research. China has successfully launched 2 taikonauts on a month-long mission into orbit. The Shenzhou 11 spacecraft blasted up from the Jiuquan Satellite Launch Center in the Gobi Desert aboard a Long March 2FG rocket.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 点火！起飞！起飞！ T0 07时30分31秒409毫秒 T0 07时30分31秒409毫秒。滚长光学跟踪正常，东风飞行正常，雷达跟踪正常，遥测信号正常。
The 58-metre-tall Long March 2FG was launched on a southeasterly trajectory towards the Yellow Sea. Its 4 YF-20B nitrogen tetroxide burning liquid-fueled strap-on boosters were jettisoned just over 2.5 minutes into the flight, followed a few seconds later by the core stage, which is also fitted with a cluster of 4 YF-20B engines. The single nitrogen tetroxide burning liquid-fueled YF-24B upper stage engine was then ignited to carry the 8.1-ton Shenzhou 11 capsule into orbit. The Russian Soyuz-based Shenzhou 11 separated from the Long March 2FG upper stage 9 minutes and 45 seconds after launch. The capsule then unfolded its solar arrays and began its 2-day journey to rendezvous and dock with the Tiangong 2 orbiting laboratory, which was launched last month into a 393-kilometre high orbit. Once docked, the crew will enter the Tiangong 2 for a month-long stay, testing the orbiting outpost's life support systems and conducting several human spaceflight experiments. Limited supplies meant that in order to achieve their planned 30-day stay in orbit, Beijing was forced to reduce the crew's size from the usual 3 down to just 2 taikonauts. The highly secretive Communist government has kept details of the mission, which represents Beijing's 6th manned spaceflight, under tight security. China conducted its first manned space mission back in October 2003. This latest mission is designed to test key technologies needed to allow China to build its own permanent space station, which is expected to be ready for launch sometime between 2018 and 2022. Monday's flight was also the 237th flight of the Long March rocket series and China's 15th orbital launch this year. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine. This month, looking at whether the next generation of supercomputers will be able to handle the mega streams of data expected from the next generation of giant telescopes like the Square Kilometre Array.